There was a bug in my finite state machine code back in episode 5. Did you catch it?
Okay, I cheated a little. I added a note pointing it out after I recorded the episode.
In that episode, we were operating on a human time scale. Having the LED on for 1 clock cycle longer than intended wasn't a big deal. Our eyes couldn't really tell the difference. However, if you're trying to meet very strict timing requirements, 1 clock cycle might be a big deal. You could miss a sampling period, or maybe inadvertently slow everything down.
To debug hardware operating at many kilohertz or megahertz, you often need some fancy equipment like an oscilloscope or a logic analyzer capable of sampling at least at those rates. As you likely noticed, synthesizing and uploading your design to the FPGA can take some time. Instead of trying to find bugs using real hardware, we can save a lot of time by writing code that tests our modules, simulating them, and looking at the output with a waveform viewer.
In this episode, I'm going to show you how to create basic test benches in Verilog, simulate your designs with Icarus Verilog, and then view the output waveforms using GTK Wave. Let's jump in.
Just like we did with our top-level design, our test bench will instantiate the module we wish to test. You will often see this module called the Unit Under Test, or UUT. Note that you can test several modules at once in a test bench if you wish. We'll stick to just one module for now, though. In the previous episode, we used the top-level design to connect multiple modules together and connect the input and output signals to our physical pins. We don't have physical pins in a test bench as it's all simulated. So we use the test bench logic to drive the input signals. We can add glue logic if we want, but we mostly care about toggling the input pins on the test module so we can measure the output waveform to see if it matches our expectations. Note that for the test bench, we have access to parts of Verilog that do not necessarily need to be synthesizable. For example, we can use delays and for loops that help us create waveforms. However, a synthesis tool would not know what to do with those commands as they're not intended to be translated to actual hardware on the FPGA. Here's how we'll simulate our design. We'll first write or copy an existing module that we wish to test. Next, we'll write our test bench using Verilog, which instantiates our module and toggles the necessary signals to perform the test. Then we'll use Icarus Verilog to simulate our test bench. The simulator will output a value change dump file that logs all of the signal changes in our test. Note that you often need to know which simulator you are using, as that can affect some of the functions and keywords you use in your test bench Verilog. Finally, we view those signal changes by loading the dump file in a waveform viewer, such as GTK Wave. Let's see this in action. As we've done before, let's go into our Appio project directory into iStick. And I'm going to create a folder called div testbench. We're going to be testing our clock divider here. In the previous episode, we created a top-level design around a couple of clock divider modules that we instantiated from this source code, from this Verilog code. I'm actually going to just copy that clock divider module, and we're going to put it into our test bench project right here. Feel free to open this up and look through it. You can see that I've already fixed my bug here by adding a -1 to this default parameter, but everything else should look the same. It's just a very simple clock divider. I'm going to call it clock div and give it the _TB for testbench.v. In reality, it doesn't matter what you name your test bench if you are calling Icarus Verilog on its own. However, since we're using Appio, Appio looks for this particular _TB suffix on your Verilog file to note that it is a test bench. So if we're calling Appio sim, your file must be named with this _TB to work. Let's go ahead and open up our clock divider test bench. The first thing you want to do in most test benches is to define your time scale. This is similar to setting your, say, horizontal axis on your oscilloscope to determine how much you zoom into your waveform, essentially, but we actually have the chance to view different scales when working with the test bench. This just tells our simulation software how it should treat things like delays. Note that the backtick character is a compiler directive. This tells Icarus Verilog to do something. This is one of those times where you need to know your particular simulation software. In this case, it's going to be iVerilog or Icarus Verilog, and this compiler directive means something special to Icarus Verilog. If you're using a different simulator, this particular timescale keyword with the backtick in front of it may not work, so pay attention to which simulator you're using. The first number is the units of time. In this case, 1 unit is a nanosecond. Anytime we set a delay in this Verilog, those units will be in nanoseconds. In particular, 1 unit is 1 nanosecond. We could use 10 nanoseconds, so 1 unit would be 10 nanoseconds, and so on. We then use a / and follow that with the precision. This means if we use fractions of a unit when we are talking about delays in our Verilog, then this determines the amount of precision that's allowed. Things will be rounded to 10 picoseconds in this particular test bench. You can use higher precision in your timescale, and this tells the simulator that it should slice things up in smaller chunks of time. However, it means that it will require more memory and hard drive space when you go to save all of your waveforms in a dump file. We then define our test bench just like we would any module. However, note that we have no ports in our port list because there are no inputs and outputs for our test bench. Everything is contained internally. We then define our internal wires and registers just like we've been doing for our other Verilog modules. In this particular case, we want to name the output signal as out, and we're going to register our clocks and resets so we can control them a little more easily. Additionally, I'm introducing this concept of setting an initial value. Clock and reset should be tied to 0. This is different than what we've been doing before, where we reset our values to 0 based on some external reset signal. Since everything is internal to our test bench, we need to set them to 0. Sometimes this works if you're trying to synthesize code for actual hardware. It depends on what you're trying to do and the particular synthesis tool as to whether you're allowed to set an initial value. In our case, it should work with simulation, so we can go ahead and set these signals to 0. We don't necessarily need to define our simulation time as a local parameter, but we can if we want it to appear closer to the top of our code. In this case, the duration is set to 10,000 units. These units are multiplied by our time scale, in particular the units of time, given by this compiler directive. So 10,000 times 1 nanosecond becomes 10 microseconds. This is the total length of time that our simulation will run. If you let it go on indefinitely, it will go on indefinitely, and the dump file will just start taking up all of your hard drive space. So it's a really good idea to limit the amount of time your simulation runs. Next, we're going to generate our clock signal. Remember, we don't have a real physical 12 megahertz oscillator to work with, so we're going to try to get something that's fairly close by writing some simulation code. Now note that this code won't be synthesizable in actual hardware, but it's great for a test bench. All we're going to do is toggle that clock line or clock registered element high or low once every 41.67 nanoseconds. We multiply it by 2 because when we toggle it, we have to toggle it twice in order to complete one cycle. So we toggle it once every 41.67 nanoseconds. We do that twice for a complete cycle. 1 divided by that period comes out to be something pretty close to 12 megahertz. We can't get it exactly on 12 megahertz, but this should be enough to perform some measurements. A delay in Verilog is fairly simple. We just write the pound or hashtag sign followed by the number of time units we wish to delay. In this case, we're going to delay 41.667, or in reality, we're going to tell the simulator that we want to delay by that amount. 41.667 means delay by a number of time units as given in our time scale. So in theory, this should be 41.667 nanoseconds. However, because we set that 10 picosecond precision, the 41.667 is rounded to the nearest 10 picoseconds. So in this case, 41.667, it's rounded to this second 6, so this becomes 41.67 nanoseconds. After that delay, we simply toggle the clock line. Notice that this always block does not have a sensitivity list. When we're doing simulation, we can do things like this that occur in parallel to everything else, and it just does whatever we tell it because it's an always block that runs always, essentially, without any sort of sensitivity, although you could include a sensitivity list if you wish. However, we don't need to. This just says run this forever. This is basically the same as a while one loop or a while true loop, where it delays for some amount of time and toggles our clock line and does that forever as long as we're running the simulation. Now we're going to instantiate our unit under test. Make sure that the module name matches up with the module name of the module we wish to test. In this case, it's clock_divider. We are going to define the parameters. In this case, I'm going to override the parameters that are set by default in the module. I don't want to do this on human timescale because our dump file would be huge if we're trying to manage both a 12 megahertz clock and wait for, I don't know, a quarter of a second or half of a second. Our dump file would be massive if we're trying to wait for 6 million time units or clock cycles for our input clock. So I'm going to change the count width to be 4 bits, and I'm going to change the max count to 6. Let's bring up my calculator here for a second. Let's figure out the period of my 12 megahertz clock that's going into the clock divider. So that's 8.33 times 10 to the negative 8 seconds for one period. And I want to count 6 of those in order to toggle the output divided clock from my clock divider. In theory, if I put 6 in here, it should give me, this is milliseconds, this is microseconds, so half of a microsecond is what we're looking for. So that's where I put 6 in here. I want to get half of a microsecond between toggles of my output divided clock. I will name this instantiated unit under test, or UUT, and now we connect up the ports. Just like we did in the previous episode, we're just going to connect the names of our internal signals and registered elements to the ports defined in our port list of the module. Because we're not using initial values in our clock divider that's going to be built into actual hardware, we need to pulse that reset line. So after 10 time units, we're going to delay that amount. We're going to force the reset line high. We're going to wait 1 time unit, which is less than a clock cycle, but because the hardware is set up in our module, the positive edge of the reset line should reset our counter anyway. And we're going to set that reset line back to low so that everything will run according to how we set it, where it starts dividing our clock. This initial block ideally only works in simulation. You should not see initial blocks inside of synthesizable code. That's because initials only run once and then don't do anything. In this case, we just want to pulse this reset line once and be done. At this point, Verilog almost looks like a scripting language, less so like an HDL or hardware description language, because this part is going to be, or would be, very tough to synthesize. Note here that I'm doing another initial block. Initial blocks and always blocks, these run in parallel. Much like having several always blocks in your synthesizable Verilog code, these will execute at the same time. So these 2 initial blocks, including this always block, start running at exactly the same time. So at the very beginning, this will pulse the reset line, and the clock will start going, and we're going to start running the simulation where we track how these values change, our registered values and our signal values, and we're going to put them all into this value change dump file. The $sign denotes a system task or function. This helps control parts of the simulation, and just like our backticks, it is not synthesizable. This is part of that scripting idea of Verilog, where we're telling the system to do something. In this case, we're going to output or dump our file, our simulation results, to this file, this .vcd file. The things stored in this file should come from this dump vars or dump variables command. Here we're telling it to watch the clock divider testbench, which is our testbench module given here, and any of the signals such as out, clock, and reset should be stored, or your values for those signals should be stored inside of this .vcd file. The 0 here denotes how many levels it should look in for the modules. In this case, 0 says look at all the levels. So if you say 1, it will ignore the signals that are found within our unit under test. In this case, our clock divider. It won't go in and watch these signals. However, if you say 2, it will go 2 levels deep, which includes this test bench and the clock divider module. If you instantiate another module inside of clock divider, 2 will not watch those. You could do 3 to watch those variables, or signals and register values, I suppose. Generally, you will see 0 if you want to watch everything, which includes all modules, regardless of how many modules deep you have nested inside of other modules. You'll see 1 if you just want to watch the variables inside of your test bench, and sometimes 2 if you want to watch those in your unit under test. But we're going to stick to 0 right now to be very verbose. 0 means dump all the variables that it finds in the testbench module, as well as all the variables in all lower level modules instantiated by this top module. This is the most verbose if you want to record everything that's going on. Next, we're going to use that # or hashtag sign again to say wait for a given amount of time, and duration is given by 10,000. So 10,000 time units, and notice it's in these parentheses, which is the same as just dropping that constant value in here, and then delaying for that amount. We're going to print this string finished to the console to let us know that the simulation reached this point. And we do that with the $display command, and then we call $finish in order to end and close out the simulation. If you forget to add this, you might find that your simulation will try to run forever. Let's save this and give it a shot. We will open up our terminal and navigate into our project directory. In there, it's a good idea to verify, but first, Appio still wants me to initialize a board, even though it's not completely necessary, but that's how Appio operates. This will create that .ini file telling Appio that, hey, I'm using an ice stick, but there are no physical pins. Remember that we don't have a physical constraint file here because we're not actually going to send this to our hardware, we're just trying to simulate it. If you verify, it should succeed, but you'll get a warning that there is no physical constraint file, and that's okay because, like I said, we're just simulating. Now we can call Appio sim. If you look, that will call iVerilog, which is Icarus Verilog, denote the output as this .tb.out file, and it's going to look for this _tb Verilog file along with our other Verilog files to use as modules inside of that test bench. So if you don't include this _tb, you might run into issues if you are using Appio. If you call iVerilog directly from the command line, you can specify where specific test benches are and where your modules are. iVerilog will run for a little while, and it will output things in this output file and dump the value changes into this .vcd. It will then open this .vcd using GTK wave, and that's where this GTK wave command comes in. Once that opens, you should see something like this. On the left side, you should see your test bench. Click the plus to bring it down. You'll see your unit under test. And this is where we can watch the signals in your unit under test. You can also watch the signals in your test bench if you wish. So you have access to both sets of signals. In this case, I want to watch my unit under test. So I will click on clock. I will insert it. You'll notice here that I'm viewing 3 picoseconds. So I'm going to zoom out, and I can also use Control and my mouse wheel to zoom, and I can slide around to view my clock signal. I also want to view the counter inside of my clock divider, so I'm going to insert that, and you can see how that is counting. And in fact, If you come over here, you can see that it is an unknown value at the front. So let's insert our reset signal. When we insert our reset signal, you can see that the reset signal goes high right at the point that the clock value gets initialized to 00. So that reset signal is doing its job. You can right-click in the viewer to drag a marker around, and that will give you some time up in the right-hand corner to tell you where that marker is placed. In this case, this is happening at about 10 nanoseconds, and it's giving you things in picoseconds. The other thing I notice is that if you bring your mouse pointer to a particular waveform, it will try to snap to any of the edges. So you can see it snapping to reset. And if I zoom out, I can drag it across the clock signal and it will snap to the edges of my clock or where the values change on my counter. Let's insert our output signal. And you can see that indeed I have a divided clock, and that is fantastic. However, I can use my middle mouse button to place another marker. You can see this marker is white instead of that red or pinkish color. And I'm going to snap this to the rising edge of my divided clock, and I can drag my pink marker around. So I'm going to scroll over and drag my pink marker to the other edge of that divided clock. And there is a problem here. You can see that it's a little more than half of a microsecond, where we wanted this to be half of a microsecond. If I drag it back, you can see that this is where the half of a microsecond should have occurred, and the divided clock should have dropped down. What this says is even though I calculated 6, it really should be 5, and that's because the counter starts at 0. That's where my bug is. So if I want to count to 6 for my divided clock to make the toggling happen every 500 nanoseconds, it really should be 6 minus 1. That's my bug, and that's why you now see a -1 in all of my max counter code. Let's go ahead and fix that. I'm going to exit out of this. Sometimes GTK wave gets stuck, so I'll give it a Control-C. You'll notice that there's an error opening the save file. In this case, it's just a warning, which means you can ignore it. You can save the waveform setup as a .gtk wave file or .gtkw. If you save your settings from GTK wave in this file, you won't get this warning anymore. I'll show you that in a minute. Let's go back to our test bench, and where we see our 6, let's give it a 6 minus 1. Let's save that. Open up our terminal. We'll do Opio Sim. That will run the simulation and open up GTK Wave. You'll see that my waveforms are no longer here. I'm going to go to my unit under test. I'm going to select my clock, my counter, my out, and my reset. I'm going to insert those, and I'm going to zoom out so you can see the divided clock again. Now, I'm going to place my marker at the beginning of this divided clock, one of these rising edges. I'm going to come over here and place another marker at my falling edge. And as you can see, that toggle time is now 500 nanoseconds, just like what we actually wanted. So the fix is to now put that -1 for all of our max count parameters when we're using the clock divider. We just have to keep that in mind. I hope you can see how simulation can help you a lot to find some of these bugs and fix them without having to go through the effort of hooking up actual hardware and synthesizing your code to send it over to your FPGA every single time. Simulation is an incredibly important part of hardware design when it comes to FPGAs. In fact, when you start looking into complex designs, you will often find unit tests written for the individual modules for that complex design. And in fact, it can get even more complicated where you can start scripting your test benches and having your test benches automatically verify what it's expected to see in the modules. So it's just pulsing a line whenever the unit under test does what's expected. It's a complete self-test, and you can have a full scripted suite of these self-tests to verify your complex design. But we won't get into that as things can get complicated quite quickly, but that is generally considered good hardware design when you unit test all of your different modules and different parts of your design. I'm going to save my GTK wave file. All this does is just save which signals show up. In my div Testbench, I will save that file, and now when I exit here, I've got everything closed, you'll see the error show up again, because this error shows up when you try to load GTK wave. But when I simulate, you can see that GTK wave loads, and I'm seeing exactly what I saw last time because I saved those settings. Now when I close it, that warning is gone. Your challenge is to write a test bench and simulate your button debouncing code from episode 5. Note that you might need to change some of your debounce code to make it work better as a module. Each time the increment button is pressed, meaning the signal goes from high to low, and stays there for some time, the LED counter should go up by 1. Note that you can also view the internal states of your state machine. You might need to make the max clock counter a parameter instead of a local param, so you can set it to something like 400 microseconds instead of 40 milliseconds. Otherwise, you might end up with a huge VCD file if you try to do this with a 12 MHz clock. For some hints, note that for loops work in Testbench code. You can also use the keyword integer to store integer variables in Verilog. Finally, see if you can figure out how to create random numbers so you can emulate button bounce or noise each time the button is toggled. As usual, I'll provide a link to my solution if you'd like to compare answers.
In the next episode, we'll see how to use various types of memory in an FPGA so you can store some data. Good luck, and as always, happy hacking!